This is going to be an explanation of how to derive the potential as a function of radius for the lab that we did. We did this in class today on the 19th of February, and the surface that we chose to use was a cylinder. I am going to explain what we did in class today and use this as a template to help you with your spherical derivation. So let's start by looking at our setup. So remember that our electric field went from our high potential, which is that center electrode, to our lowest potential, which was out on the outer ring. Remember that outer ring was at our 0 volts or 0 potential. So the electric field goes from inside to outside. And I've got a couple of things labeled on here. You'll notice this green dashed line. That green dashed line is the surface that we are choosing to use. So the Gaussian surface that we are using for this one is a cylinder. So you can think of a soup can kind of coming out of your screen, and the electric field that's represented in red is going to pierce the soup can label part of that cylinder. And so we're going to use that surface to derive an expression for the electric field, and then we'll use that to determine the potential. So there's 4 steps to this process. Our first is to use Gauss's law to derive an expression for the electric field, and we're going to do so in terms of Q, R, and then this guy is actually L, which would be like the length of the cylinder, and the length of the cylinder is going to be what's actually like coming 3-dimensionally out at you. A couple of other things that are labeled. The distance from the center, and that should be all the way from the, nope, that's actually on the, no, I think we want that on the edge there. I'm just making sure that's in the right spot. So from here to here, so from the edge of that inner dot to the Gaussian surface, we're going to call that R. And then our distance from the center out to the edge of that inner circle is little a, and then from the center out to that outer edge is going to be B. And actually, you know what? That radius is going to be all the way from the center. So let's make sure that we're super clear on that. So we start by using Gauss's law. Notice that I've stated here that the soup can label, not the lids, is going to have the flux, because the lids are going to be like parallel to your screen. There'll be no electric field lines piercing that. The label is what's going to be piercing that. So we write down our Gauss's law, and notice the electric field is perpendicular and uniform at that outer ring, which is why we choose to use it. And we need to add up the areas that the electric field pierces, so that's going to be that soup can label. Then we have our enclosed charge, so that's going to be the charge on that inner circle, and then our permittivity constant. So next step down, notice that this dot product is a positive value since the electric field vector and the area vector are in the same direction. And the area, when we add all of those up, which is what that loop integral means there, we have the area of the soup can label. So that's 2 pi r L. And remember, our first step was to try to get an expression for our electric field. So we just rearrange and come up with this expression. Now notice I pulled all this jazz out in front. All of this is a constant. This is our variable, right? So if we go back to our goal step is to derive an expression for electric field, and we've got these terms here. That's going to be a constant. This is going to be a constant. R is what that variable is. We're going to kind of pull that all out to the side. Right? So then let's take a look at our next step. I'm going to cover up some of the screen since we don't need it all. We are going to derive an expression for potential difference, again, in terms of Q, L, and R. And this time we're going to use the expression of the potential with the electric field and the radius. So notice a couple of things. This is a potential difference, which is what that delta tells us. And then we've got this negative out in front because as you go down the electric field or go with the electric field, the potential decreases. It's like going down the hill. And then we've got electric field, and then this means we're going to like take a pathway from one linear place to another. So notice it's not like a loop or a surface like we've been using. It's called a line integral. All right, so in our last slide, we have an expression for our electric field. We're going to use that in our new relationship. So we're going to substitute that in here for that E. So when we do that, you're going to notice that we have our limits of integration. So our limits of integration in this case are going to be our outside radius. So that's that outer ring to our radius, that cylinder that was in green on that other slide, that's somewhere between the outer ring and that inner dot. And this we said was just a number, just a constant. So that's actually going to come out in front of the integral. And we are left with this expression. So our potential difference is equal to the negative of this stuff here times the integral from the outside edge to r, 1 over r dr. So then we integrate that, look in your table or look in your information on your green sheet, and you're going to find that that is the integral of the inverse function is just the natural log function. And we are going to evaluate that from b, which is that outer ring, to r. And when we do that, we see that that will become the natural log of r minus the natural log of b. Now, if you're familiar with the properties of logs, that's the same thing as the natural log of r divided by b. And again, remember, this is just a number. So, like, just kind of ignore it for right now. Treat it as kind of a thing. Don't get all stressed out about it. Okay, so we've accomplished our goal for this step, right? Our goal for this step was to derive a function for potential with respect to r. All right, so we're ready to move on to our next step. And I'm going to cover that up again. So our next step is going to be, we're going to use our expression from step 2, so the one we just found, and then the measurements of the outer radius and the potential difference maximum. So that would be like when you put your probes on the outer ring and the inner ring, what that potential difference was. So it's about 10 volts. We're going to use it to find the constants in our equation. Okay, so we start back at our function that we just found, right? And that what's circled in green is that kind of thing that we were going to try to find. That's a coefficient, right? So we're just going to call it x, and our job right now is to find this. Okay, we're trying to find this business right here. So at the position of the radius here, when it's at position A, the difference then between the outer ring, which was at location B, and then the inner ring, which is at location A, the difference between that is 10.01 volts, or whatever you guys measured it to be. So each lab will be slightly different. I measured mine to be 10.01 volts. So we're actually going to substitute in the values for A, right? Like literally use a ruler and measure them. Also the distance for B, and then use that potential difference, substituting in here, here, here to find this business right here. Okay. So when we do substitute that in, so this is the radius of that inner dot. This is the radius of that outer ring. We're trying to find this big old X right here, and then that's our voltage between the inner dot and the outer ring. So when we solve that all the way down, I got my x to be 4.19. Woo-woo, right? So then we now know what that whole big thing was at the beginning, or that coefficient at the beginning of our equation. Okay, so then I rewrote. All right, so then we rewrite. Now check this out. So we have our potential difference is equal to the negative of the 4.19, so that's that x that we found before, times the natural log of r. Okay, that was our variable, divided by our constant, which is b. And in this case, our b value stayed the same. That's the radius of that outer ring, right? Okay. Now, when we want to go substitute this into the computer or put that into our computer, it's kind of difficult to type in something like this. So what we're going to do is we're just going to turn this into a coefficient or a number in front of the r. So it's basically 1 over 0.076. And we rewrite. And then this, right? This is going to be our function. So this is, we have now reached our goal, which is the function of the potential difference with respect to R, or how the potential difference varies with R. And we are ready to put this into Logger Pro and do a manual fit. And you can find the next video again on my Canvas homepage for that.